So is my screen visible?
Yes, sir.
Okay, okay, great. So let us start with the Bernstein Vazirani and Deutsche Jodza. You all have taken the derivation. You have seen Qiskit implementation. It's very straightforward. Whatever we implemented in theory, we also implemented it on Qiskit and verified our results. Same for both the algorithm Deutsch and Deutsch Jodza. So we are also going to do the same thing for Bernstein Vazirani and Simon's algorithm. So tomorrow we are going to see the Qiskit version of Bernstein, and tomorrow we are also going to complete Simon's algorithm theory plus practical implementation with Qiskit. So let us start again. Uh, it is very similar. So let us see. So just a moment. I think I need to admit also, right? So need to keep that also in mind. So whenever people arrive, need to admit them. Yes. So what will the Bernstein Vazirani algorithm does? Huh? What will it do? Bernstein Vazirani algorithm, right? Bernstein Vazirani algorithm. Okay. This is a special case of Deutsch Jodza algorithm. Okay. What is this? This is a special case. Okay. Special case of Deutsch Jodza. Okay. It is a special case of Deutsch Jodza algorithm. Okay. In which now what happens here, we are going to define a specific function. Okay. In the case of Deutsch Jodza, we were saying that we have some sort of unknown function. Okay, we do not know what is that function, whether it is a constant or balanced. We were trying to find out whether it is a constant or balanced. Okay, by the unknown function. And the way we were constructing those unknown function was using a particular pattern of CNOT gates, or sometimes we use X gates for the constant oracle. Sometimes we do not use X gate for constructing the oracle, etc. Okay, we have already seen for Deutsch Jodza, which is a generalization of a Deutsch algorithm. We saw that in the balance case for Deutsch Jodza, we are able to wrap X gates around the controls of the C naught wherever we have the input as 1. So we saw all those stuff. Okay, and now what we are saying is that now we are going to derive a special case of Deutsch Jodza in which fx is equal to, fx is linear, basically a dot x. Okay, fx is what? Fx is linear, a dot x, where a is equal to a n minus 1, a n minus 2, and so on up to a naught is a what? Is a n bit. It is a n bit binary number, right? This is a binary number representation, right? Binary number, we have seen these things. Okay, binary number. Now what is the problem? Now let us again write the problem statement, just like we did for Deutsch and Deutsch Jodza. Okay, given an unknown linear function. Okay, we have given an unknown linear function. Okay, we know that the function is linear. Okay, this information we have. Okay, let us generalize that function x n minus 1, x n minus 2, so on up to x1, x0. Okay, of n inputs. Okay, n inputs you have seen in Deutsch Jodza already, right? That are known to be defined by mod 2 dot product, okay, with n binary digit constant a. Okay, so what basically it is, like, saying that a dot x. What is a dot x? Okay, what is that dot product? That is a mod 2 dot product. It is saying that it is a mod 2 dot product, and where a is the constant. Okay, that is the problem statement. So therefore fx is equal to a dot x, okay, which I defined in the statement above, right? That is the a dot x. And now it says find a. Okay, what is the problem? Find a in one query. Find a in one query, and we already know that for Deutsch and Deutsch Jodza, all the searches which happen, that only takes one query, right? We have already seen that. Why? Because of quantum parallelism and quantum interference which we have in both Deutsch and Deutsch Jodza. Okay, because of that, find a in one query of the quantum oracle. Okay, find a in one query of the quantum oracle. Now let us start doing our analysis for the Bernstein-Vazirian. It's a very short algorithm. It's not very large actually. So let us start doing the analysis. The analysis will go very similar to what you have done in Deutsch Jodza. Okay, so there is not so much explanation needed. Even the circuit also looks like Deutsch Jodza. Okay, because indeed it is a special case of Deutsch Jodza, right? Only thing which you are doing is you are just defining a linear unknown function. Okay, you have the function unknown, but you say that it is linear, and where a needs to be found. Okay, the value of a needs to be found by only one query of the quantum oracle. So basically coefficient you need to find, the coefficient attached with the variable x. Okay, that is what we are trying to say. So let us start doing the analysis. So Bernstein Vazirani quantum circuit analysis, right? So quantum circuit analysis. Okay, very similar to like Deutsch Jodza. Please turn back to your notes which you have studied last week with me, and take a look at the notes carefully. What we are doing, it's a very similar kind of circuit which we have done last week. So h tensored n for n qubits. Okay, and then we have get 1, and then again we apply Hadamard. This is the same step like Deutsch Jodza, you can recall. So, and again this is our oracle. Okay, and we are also going to divide this because we will analyze this, right? Just as we have done for Deutsch Jodza. So, and then here we have h tensored n, and then nothing we will do in the second one. Okay, and then we have measurement, and that's it. Okay, so same kind of thing which we were doing, very similar. So therefore, like not much, you do not have to struggle too much today basically for this algorithm. Very similar to Deutsch Jodza, so you can keep referring back to Deutsch Jodza derivation while I am doing this. Okay, and now what happens? So now let us say, like, let us name these states also. Phi naught, this is phi 1, phi 2, phi 3, and phi 4. Okay, so again, so let us take some notes. So top register. Okay, we have the top register which provides the quantum parallelism. Okay, which provides the quantum parallelism. We are already aware about this, and the Ket 1 in the bottom, in the bottom offers offers a phase kickback. Okay, what is phase kickback? As it is a self-explanatory term. Okay, where the phase, okay, but the phase associated with the bottom register, second register, is kicked back into the first register. Okay, therefore the information which is present in the second or the last qubit, okay, where it is ket 1, is transferred to all the qubits in the first register. That is what is called phase kickback. That transfers information about f, okay, that means the function, from target, that means which is the last qubit target output, okay, to the first register, okay, to the first register. Okay, and already you are familiar, like, this is what we have discussed. This is the first register, and second register has only one qubit, right? So we have already discussed this, so not going to touch upon it again, but it is already understood here, right? Because this is a special case of Deutsch Jodsa. Okay, now let us try to do the analysis. So we have already drawn the circuit, so let us start with step 0. Yes, step 0. What is step 0? Initially we prepare the state. Okay, initially we prepare the state. Ket phi naught is equal to ket 0 tensor. So like same step which we have done for Deutsch Jodsa. Then step 1. Okay, in step 1 we will apply Hadamard, right? We have applied Hadamards. Okay, so apply Hadamards to both registers. Okay, apply Hadamard to both registers. So therefore ket phi 1 will become H tensor n applied to all the zeros tensored with H with ket 1. Okay, and therefore now again, like, again, this is again the same formula which I have already taught you last week. What was that formula? Hadamards applied to n qubits, right? That those formulas are very important, and I especially boxed them. Okay, there was a reason to do that, because we used them several times. Okay, so that is why you should definitely try to take a look at those formulas again. So again, directly using that from that class, 1 by under root 2 to the n summation x is equal to 0, and then 2 to the n minus 1 ket x, and also Hadamard applied to ket 1, which is your, which is what, ket 0 minus ket 1 divided by root 2, which is also your ket minus state, right? So this is the step 1. Now what will happen with step 2? The unitary oracle will be applied, and this time it is a dot x. Remember that. Okay, this time unitary is a dot x, right, where a needs to be found. So step 2. So it is not some generic thing. Okay, this time we have a, like, it is like a specific criteria we are following this time. Linear function. Okay, so now step 2, the UF unitary oracle is applied to all the qubits, right? The UF unitary oracle is applied to all the qubits. So therefore, phi 2, what will happen to phi 2? UF applied to ket phi 1, right? And then what will be the formula? 1 upon under root 2 to the, again, I'm using those same formulas, okay? So not going to mention them, but yes, please go through that notes. Hadamard applied to n qubits, okay? That's very important. Minus 1 a dot x, okay? And then x, right? And I mean, like, if you compare this with Deutsch Jodza again, like, you will start seeing the similarities of, like, how it is coming into the picture, okay? Then step 3. Okay, step 3. What is step 3? Let us see step 3. What will be step 3? It will be applying Hadamard gates on the first n qubits, basically the first register, right? So apply Hadamard gates, okay? Apply Hadamard gates on the first n qubits. That means the first register. So what will happen? Get phi 3 is equal to h tensor n tensor I, right? Because doing nothing means identity, and we are not doing anything with the second qubit. So doing nothing means applying identity to get phi 2. And again, from Deutsch Jodza analysis, you can again get, like, again, a similar kind of expression you will achieve. Okay, 0 comma 1 to the power n. And then inside this box you will have x belonging to 0 comma 1 n and minus 1 a dot x plus x dot z. Okay, and get z is also there, and that minus is also there. Okay, so now what is going to happen? Now again, like, we have reached a similar kind of stage which we reached in the analysis of Deutsch Jodza, right? Where I spent a lot of time in explaining you what is the whole bit string of ket zeros, okay, and how the amplitude, okay, by quantum interference, how the amplitude matters there, okay, the coefficient and the probability occurrence. The probability occurrence is directly depending on the coefficient attached with the quantum state, right? And therefore, I explained you that for the balanced, you are not going to see the all ket zero bit string. That means probability of occurrence of that is zero and its coefficient turned to zero, right? When we calculated, we saw that the coefficient turns out to be zero because all the terms balances out and cancels. Some becomes zero, some becomes one, some becomes minus one, and like that, and it cancels out, it balances out. Therefore, we saw that are now a similar kind of analysis we are going to do here, but not constant or balanced this time. With this time we have a, right? And therefore z should take the value of a. We want that the z, because z is the variable ket z, right? What is this? Ket z, right? This is the variable. Now we want that this bit string's amplitude of having a increases. That means the probability of measuring the value of a, which we want, okay, should increase. How will it increase? Once the amplitude of ket z increases, right? Then only we will get to know that, yeah, for z is equal to a and then z not equal to a. So therefore there are two cases now, okay, very similar to Deutsch Jodza, but in that case we were having constant or balanced. It was a general case, this is a special case. Okay, so please note down now step 4. Step 4. So finally measurement of first n qubits is made in the computational basis. Okay, now we are going to see two cases. Computational basis. Okay, so let us name this function 1 upon 2 to the n summation. So we are considering this one basically, like just we considered for Deutsch Jodza. Okay, keep flipping pages back to Deutsch Jodza and try comparing this with that. Okay, you will automatically understand and observe what is different and what we are doing here. Okay, get set. We are only considering that one. Okay, and we are also taking this one also 1 upon 2 to the n. Look at this dot 1 upon 2 to the n. Okay, we are also taking that. Now two cases arise, so let us solve those two cases. Okay, so let's scroll down a bit more. Okay, so two cases, so let us take the simple case. So z is equal to a, so therefore c of a summation. So we are just going to put into that formula c of z, that one, because that's the major amplitude which is associated with ket z, which is the variable, and that is that ket z we want that it takes the value a. Okay, because we are looking after a, right? Find a. Okay, that is the problem statement, right? Find a. So minus 1 a dot x plus x dot z is equal to, and then once again, like as you solve it. Okay, I'm not going to solve it like step by step. You can do it in your free time. So I'm directly going to write the result. Okay, but it's very understood. I have done the solve for Deutsch Jodza, so it should not be too much difficult. Okay, therefore c of a divided by 2 to the n, because there was 1 upon 2 to the n also, this one, don't forget this. It gives you 2 to the n divided by 2 to the n, which is 1. Okay, so again 1 is coming. Okay, 1 is coming means, again this is very similar, like constant case. This is like very similar. Okay, so you can maybe write it similar to, if you're like trouble, if you're facing trouble in remembering, like you go, okay, like what is this case. Okay, so Deutsch Jodza constant case. Okay, similar to Deutsch Jodza constant case. Okay, in this way you can remember. Maybe you can note this down in your notes so that you do not forget. Okay, then next is z is not equal to a. This will be what? Similar to balanced case, right? Similar to Deutsch Jodza balanced case. Okay, Deutsch Jodza balanced case. Now, so what will happen? So there will be same number of x such that a dot x becomes 0 and such that a dot x becomes 1 in the summation. So basically this is the same reason which we saw in Deutsch Jodza also, like cancelling out of the term, like balances out and cancels out, right? As a result, the probability amplitude vanishes. The same thing happened with due to Jones also, right? The probability amplitude vanished. It got into 0, and that's why, like we were saying that okay, we will never have a large amplitude for all 0-bit string. And if we do not have a large amplitude for all 0-bit string, that means we have some other kind of amplitude, and that means that the oracle was balanced, right? This is how, like, connect, like this is how you should always do. Okay, like whenever you have studied a past concept, try to connect it with the present concept. How is that concept related to the previous one? Okay, because many times, like, and this is true for any subject, right? Whenever you are studying a subject, try to connect it with the previous ones, then you will see how ideas flow together, right? This is for any field, whatever you are studying. This is not only for scientific field, but even for literature, arts, or any other field which you are interested. Okay, it's not necessary that you always have to study science. Okay, and then probability amplitude vanishes. So therefore now what will happen? So summation x belonging to 0 1 n minus 1 a dot x and then minus 1 x dot z becomes 0 for z not equal to a. So for example, let us take an example calculation. So let us take example. Okay, let us take a example. Let's say a is 0 1 and z is equal to 0 0. So basically we are searching for 0 1, but z turned out to be 0 0. So what will happen? So summation x belonging to 0 1 n, okay, minus 1 a dot x and then minus 1 x dot z, which is equal to, and then like start calculating minus 1, like 0 dot 0. Okay, basically just start taking the product. Okay, like 0 0 will go with 0 0. Okay, then 1 1 will go, the 1 dot will go with 0. Okay, and then similarly minus 1 x dot z. Okay, so again what will happen is that 0 dot 0 XORs with 0 dot 0 plus. So basically just take x as 0. Okay, and then you should take x as 1. Okay, so this will only go for n is equal to 2, because I mean there are two qubits, right? A is equal to 0 1, z is equal to 0 0, two qubits, so there will be four sum parts. Okay, this is the first sum, right? This is the first sum. Then second sum will be minus 1 0 dot 0 XORed with, because remember it was a mod 2, right? So what is mod 2? XOR operation. So remember that was also mentioned in the problem statement. So XORed with 0 dot 0, and then again like this is the second term and so on. So like now we will have plus, this is the third term. Okay, minus 1 0 dot 1 XORed with 1 dot 0, and again like x's value you are taking 1 dot 0 XORed with 0 dot 0, and finally so two qubits, four terms, so four sums. So therefore this is the last sum, minus 1 0 dot 1 XORed with 1 dot 1 and then minus 1 1 dot 0 XORed with 1 dot 1 dot 0. This is the final term. Okay, and once you start calculating it is very easy. So you will see minus 1 to the power 0 minus 1 to the power 0 plus minus 1 to the power 1 minus 1 to the power 0 plus minus 1 to the power 0 minus 1 to the power 0 plus minus 1 to the power 1 and minus 1 to the power 0, right? So this is what you are going to see, and therefore 1 minus 1 plus 1 minus 1 turns out to be 0, and therefore that is indeed true. The summation indeed balances and turns out to be 0. Okay, so therefore like and like this is what Bernstein Vazirani tells you, that therefore like in this way, when z is not equal to a, therefore the probability also of measuring the z that it is indeed a will also be 0. The probability amplitude directly goes to 0, therefore you are not going to measure, you are not going to measure the a value. Okay, you are going to measure some other third party value. Basically that is what it tries to say. Okay, you will be getting some other third party value, not some not the value which you are looking for. Okay, so it's very similar to the balanced case of Deutsch-Jodza algorithm. Okay, So with this, the Bernstein Vazirani is concluded. So tomorrow we are going to see the Qiskit textbook for Bernstein Vazirani. And if you have missed anything, please note it down. Anyways, I'm going to send this, but still, if you have missed something, please note it down. It will be easy. So have you all noted down quantum circuit analysis of Bernstein Vazirani? Have you noted down the steps? Step 1, step 2, step 0? Has anyone written step 3, step 3 and step 4? Hello? Am I audible?
Yes, sir.
Hello? Yeah, have you written?
Yes, sir.
Step 4, have you written?
Not yet.
Okay, please note down step 4. From where have you left?
Step 3 is done. Yeah, step 4.
Okay, okay, please note down step 4.
Sir, can you scroll down? Actually, I'll just get shots of this so I can write them down at a better pace later.
Yes, yes, definitely. Please take. This is Z is equal to A. Have you taken the
Yes, sir.
screenshot?
Yeah,
And what about Z not equal to A?
got it, sir. Yeah,
And example, this is very important. Example.
yeah, I have this, sir.
Okay, okay, great, great. So this is the Bernstein Vazirani, and I hope that everyone is now able to connect this with Deutsch Georgia. It's very, very uh, easy to understand also. Not a very difficult algorithm, as you already saw. And similarly, the Qiskit implementation is also like that only. It's also not very difficult to understand. It's very straightforward, like Deutsch Georgia and Deutsch algorithm. So tomorrow we are going to see the Qiskit implementation, and we are going to uh, proceed with Simon's algorithm. Okay, so now let us conclude. I'm going to stop the recording here.